Everybody. So yeah, thank you for having me here. Glad to see people from two meetups here. This is really, it's an honor. So yeah, it slices, it dices, it drills, it does all those things. And so I'm going to talk about what we mean by operational analytic data stores, how this sort of fits into the big data landscape, and try to talk about things like Druid. So there's about maybe half dozen systems that are kind of similar, and try to give you a framework for thinking about how Druid fits into that world. Talk about what we do with it at a high level, and then the next couple of talks are from people at our host lift about getting into much more nitty-gritty detail about what they're doing. So let's see, who am I? So I'm Gian Merlino. I'm a committer and PMC member on Druid. Druid is a open source effort that began about 5 years ago, and it's actually this calendar year, it started incubating at the Apache incubator, so soon to be Apache Druid. I'm also a co-founder, like Mark mentioned, at Imply, a company that's built around Druid, so doing Druid and also UIs that are designed to take advantage of Druid. And me, myself, I've spent about 10 years working on scalable systems. It's really what I love to do. I love to build scalable systems. I love to build tools for people to use. So first off, just to give you a frame of reference, I want to talk about the problem that we're trying to solve with these kinds of operational analytics data stores. Then I want to talk about how we approach that problem. I want to look under the hood of Druid as an example of how these problems can be solved. And then especially for the people that are coming here from the Druid meetup, talk about future of Druid. I like to use these meetups as an opportunity to talk about the roadmap, what the community is currently working on. And then do try this at home. So Druid is open source. You can download it online. You can contribute through GitHub. And we'll talk about how you can join the Druid community. Well, you're already in the Druid community, some of you. So first off, what problem are we trying to solve? So it's really important to understand the problem you're trying to solve. Solutions without problems are fun for engineers, but they're ultimately, if no one's going to use something, why build it? So the problem that we're trying to solve is slice and dice for big data. What I mean by slice and dice is building UIs like this. These are screenshots of the UI that we offer at Imply. There's other UIs out there that have the same kind of idea. The basic idea is you're exploring through your data, you're trying to understand what's happening in your data, and you're understanding by slicing and dicing across different attributes, drilling into attributes, computing measures and aggregations, that kind of stuff. So interactive exploration is really a big part of it. The idea is that you don't just want a static dashboard. You don't even just want a real-time dashboard. The way I think about dashboards is there's a lot of technologies out there that can build even a dashboard that updates in real time, but that's not what we're looking for. We're looking for one you can drill into and really, feels like you're interacting with it and not just looking at something that's updating. And we want data fresh. So we don't just want to be able to slice and dice and filter. We want to be able to do that on real-time data. So what are the challenges with this? The first is scale. So when data is large, this is the big analytics meetup. We're targeting big analytics. When data is large, we need a lot of servers. We need something that can scale to a lot of servers. Speed is important. So for that UI I was showing a couple slides ago, we need sub-second response time. We need the ability to, when someone drills into something, when someone pivots the UI, we need the ability to draw a new visualization in a couple seconds or less, even sub-second. Another challenge is complexity. So one way that people have solved these kinds of problems in the past is by pre-computation. So basically pre-compute every possible view anyone could ever land on. And as someone clicks in the UI, load that pre-computed view. Once you have tens or hundreds of dimensions, that becomes impossible. So we can't pre-compute. We got to be able to compute these answers on the fly. Concurrency is also a challenge. So you want to handle a lot of users, maybe even a multi-tenant system where lots of different kinds of data sets and different use cases are running in the same system. And a final challenge, freshness. You want to be able to load data from not just batches, but also want to load data from streams. And what's the motivation for this? Why do we want to solve this problem? The motivation is that sub-second responses allow a dialogue with your data. The idea is that you don't want people to think like they're issuing a query and waiting for a response. We want people to feel like they're actually interacting with their data as if it's a real object, and the only way to achieve that is to have a really fluid UI powered by a really fast backend. That lets people do rapid iteration on questions. The idea is you see something, you have another question. You answer that question, you have another question. That's the idea behind drilling down and pivoting, is that every one of those is motivated by a new question that occurs based on something you saw. And the point of all of that is to remove barriers to understanding. The idea is that by using tools like this, you can get a better understanding of your data, even a really big data set. So the category of data systems that solve these problems we call operational analytics data stores, or big OLAP data stores. So some examples of these, Druid's one of them, the one that I work on. Another example is Scuba, something out of Facebook. It's not open source, it's an internal project at Facebook. There's actually been a bunch of ex-Facebookers leaving Facebook and starting startups doing things like Scuba because of how well received it was internally. Pinot, open source thing from LinkedIn. Something called Doris, formerly called Palo from Baidu out of China. And something called Clickhouse from Yandex out of Russia. So these all appeared on the scene in the last few years. And they're really a new class of data store. So, and they have a lot of things in common. They're all column-oriented, so they all are only needing to load and scan the columns that you actually refer to in a query, taking advantage of the intuition that if you have 100 attributes in your data, most queries are not going to hit all 100. Most queries are going to hit 1 or 2 or 3, and you only want to load and scan the ones that you actually need for a query. They all support high concurrency, so you want to be able to have a lot of people hitting the system at the same time and not have it fall down. Scalable to hundreds of servers and millions of messages per second of ingest, both important. They all distribute data by having a partition key for query pruning. In Druid, that partition key is based on time and then some other dimension. So it might be time and then user ID, for example, or just time by itself. The idea is that if you have a filter where, in your interactive app, filter last 6 hours, last 30 days, last 90 days, Druid can quickly filter down to just the data that matches that time range. May or may not have secondary indexes. So by a secondary index, I mean you have the primary index used for partitioning, and then you may have a secondary index underneath that. So once you find the right time partition, another index to find the right, domain or user or whatever. Druid does do that. Druid uses compressed bitmaps for that. I'll talk about that in a later slide. A common feature in these sorts of data systems, you query them through SQL. And another common feature is they're all designed to do rapid queries on denormalized data. So a lot of them don't support joins. Some of them support a limited kind of join, so just a fact dimension type join, but not two big tables. I don't know if any of them do support joins, but if they do, it's not the main use case. And certainly Druid supports only a limited kind of join. So the use cases for these kinds of things, they all have similar use cases. Click streams and user behavior is a big one. So, tracking activity on mobile apps, websites. Application performance management. So, if you have a API, you want to emit metrics every time it does something. Emit metrics about latency, how long it took for the API call to happen, how long it took to make a database query, how long it took to make a Redis query, that kind of stuff, and analyze that. Network flows, Internet of Things, sensor data, digital marketing, online advertising, and OLAP and business intelligence. So these are all pretty common use cases for this kind of technology. So I'm going to talk about Druid, which is the instance of this technology that I'm most familiar with because I've been working on it for 5 years. In Druid, we call it a high-performance analytics store for event-driven data. If you go to our website, you'll see that at the top. And I want to unpack a little bit what we mean by that. So high performance, we're targeting low query latency and high ingest rates. We're in analytics, and analytics, I mean counting, ranking, group by, time trend. Those kinds of queries are what Druid does. Data store, it stores a copy of your data. So unlike something like Hive or Presto, it's not going to query data from somewhere else. It's going to load data into itself and then query data from its own copy. That's part of how it achieves high performance. And then event-driven data. So that's fact data, like the ones I mentioned earlier, clickstream, network flow, and so on. So Druid's been around for a little while, been around for a few years. It's used heavily in production by a lot of companies. These are some logos from the Druid Powered By page. If you go to druid.io, click on Powered By, you'll see these guys. I don't think I have time today to talk about what exactly they're using it for, but if you do check out our site, for a few of these, we have information, blogs, that kind of stuff, YouTube videos about what exactly it is they're doing with Druid. But it's a lot of the stuff I mentioned earlier, online advertising, user behavior, network flows, that kind of stuff. A quote from Yahoo. This was in an InfoWorld piece that they did a couple years ago. The performance is great. Some of the tables we have in Druid have billions and billions of events in them, and we're scanning them in under a second. So this is the kind of stuff that we're trying to do with Druid. at least the way I see it, the key features of Druid: low latency ingestion from Kafka. So we have a very tight link between Druid and Kafka. Bulk load from Hadoop. We have a built-in Hadoop indexing system that runs MapReduce jobs and loads data into Druid. We can pre-aggregate data during ingestion. I'll talk about that in a little bit. That's a really cool feature. Schema light is a pretty cool feature. So the idea is that you can evolve your schemas, you can change types, you can add columns, remove columns. You don't have to alter a table or anything like that. It just affects new data that comes in. Support ad hoc queries, so that's no pre-computation, being able to do any kind of query you can think of on data once you've loaded it in. Both exact and approximate algorithms. And we can keep a lot of history, so years are okay. It's not just a system that sits on top of a stream and looks at the most recent data. It's a system that can have a lot of historical data too. So the point of Druid: make interactive data exploration fast and flexible, and power analytic applications. It's cool. So I want to take a little bit of time to go under the hood. I might need to go a little bit quickly through these. I'm not sure how much time I have, but let's just do it. So let's look at some example of raw data. So here's the data set. I'm going to talk about a few of the ways that Druid works under the hood, the storage format, the way it ingests data. So here is a sort of truncated network flow style data set. So we have a firewall action, accept, reject, what protocol it was, TCP, UDP. Of course, in a real data set, we have more columns like source IP address, destination IP address, port, but I just didn't have space for it here. So the first thing I mentioned, or the first thing I want to mention is I talked about one of the key features of Druid is pre-aggregation at ingest time. So we call that rollup. And the idea is that if you activate Druid's rollup feature, you basically tell it what attributes you care about, what you want to be able to filter and group on, and it'll do a little bit of a pre-aggregation at query time. We don't call it pre-computation because we're not pre-computing results of queries, but we are doing an aggregation along the attributes that you said you care about. So you can still do any grouping, any filtering across those attributes, and any two rows that, for example, have the same action, same protocol, same source IP, destination IP, et cetera, end up in the same Druid row. So it's a form of summarization. And in a lot of data types, especially clickstream, that's a big one where this matters, you can get pretty good compression this way. So ratios of 10 to 1, 30 to 1, depending on what attributes you decide to keep. Like every distributed database, we shard and partition data. So Druid is, its partition key is time. So we're going to partition this data based on hour in this example. So first hour, second hour, third hour are going to be partitioned separately and stored separately in separate files. If any one hour has too much data for one file, usually these files top out around about 1 gigabyte. So too much data for one file, just add another one. There's not really any limit to the amount of segment files you can have per time chunk. These segments, these file segments are the fundamental storage unit in Druid. They're immutable once they're created. There's no contention between reads and writes because of the immutability, so they can be queried super quickly. And the model is that one thread is scanning one segment. So you have all the threads, all the CPUs available in your cluster. Each one can scan one segment at a time. And so that's the way that we parallelize. That's the way we parallelize your data in Druid. The same given segment can be scanned by multiple threads. So you can't have all threads scanning one segment if that one is really hot. Another thing we do. So I mentioned we store things column-oriented. Each column is individually compressed. So the string columns are dictionary encoded, and then LZ4 compressed on top of that. We also store, so this is an example of dictionary encoding. I'm just going to, in the interest of time, skip past this without talking about the numbers. We also have indexes for fast searching and filtering. So Druid, this is the secondary indexes I was talking about. We use a primary index on time to find the segments that are relevant to your query, and then within each segment, a secondary index on any attribute. So if you're filtering on action equals accept, then we have basically a row list for accept, first row, second row, and that's stored as a compressed bitmap. And so Druid is able to go grab that row list and then aggregate the results for that row without having to do a scan of the action column. This is super powerful. It means that when you're doing drill downs, the speed of the database gets dramatically faster as you filter to smaller and smaller amounts of data. So as you make your questioning more and more precise, it gets faster and faster and faster due to the secondary indexes. So I mentioned we do approximate and exact algorithms. This is some of the 4 most popular approximate algorithms Druid has. So the first one, count distinct, that's almost the granddaddy of approximate algorithms. Hyperlog is super powerful these days. Everything supports it. We do it too. But because we're trying to be cool, we don't just do count distinct through hyperlog. We also support count distinct through something we call theta sketches. And that's like hyperlog, but unlike hyperlog, it supports set operations like intersections and differences. And that could be used for retention type analyses. We also support approximate ranking. So if you want to know top N, top IP addresses, top users, top publishers, top domains, we support an approximate ranking function that works really well on high cardinality data, and then approximate histograms and quantiles as well. I got one slide about the architecture in Druid. So the architecture in Druid at a glance. Data comes in to so Druid's a multi-process architecture. There's a few different server types in a Druid cluster. The idea is each server type can be individually optimized, individually scaled. If you're running Druid in a container or virtualized based system, then you'd probably have one kind of container for each one of these server types. Input data, whether it's files or streams, go into these Druid indexers. That generates those immutable segments, and those immutable segments get handed off to Druid historical processes. Historical processes are completely read-only. They focus totally on having super high query performance and concurrency on this read-only data. And then the query brokers query both of them. So that's how we support real-time queries. The way the Druid does real-time queries is the Druid query broker is able to query the indexer for data that's currently in the process of being indexed before it's handed off to historicals. So that's my whirlwind tour of under the hood of Druid. The next thing I want to talk about, and this is, I think, mostly for people that are here for the Druid meetup, so I'll just keep this to one slide, is the mysterious future for Druid. What's coming up in the Druid community? What are we working on? So right now in the Druid community, we're working on a bunch of cool things. One big one, parallel loading of data files without Hadoop. So right now in Druid, if you're going to do a parallel load of a ton of data files, you're basically going to be doing that with Hadoop. If you're doing a parallel stream load, it's going to be through Kafka. So Hadoop and Kafka are 2 main ingestion mechanisms. There's a lot of interest, I think, in these days. A lot more people are deploying in cloud environments like Google, Azure, AWS, and not running Hadoop at all, just storing data in the blob store that their cloud provider provides. And that's cool. You don't have Hadoop at all. You don't want to start Hadoop just to be able to load a bunch of batch files. So we're working on supporting the ability to load data files directly from some sort of cloud storage without using Hadoop. Automatic compaction. So that's a sort of the nuts and bolts feature, right? So that basically imagine a little gremlin that just goes through and optimizes your data schema so you don't have to. Smaller, faster compression. So, basically staying up with the state of the art with how integer compression is done, floating point compression, bitmap compression. So we're always sort of reevaluating those things in Druid. Performance is super important to our community. And so people are really interested in making sure that Druid's using whatever the state of the art for compression is. Subtotals, SQL grouping sets. So this is about query fusion. It's about fusing 2 queries into 1 query. So let's say you want to do a daily breakdown, a weekly breakdown, and then a grand total all at the same time. Right now, that'd be 3 separate queries, but grouping set type functionality lets you fuse those into 1 query. SQL standard null handling. So right now, the way Druid handles nulls is a little bit idiosyncratic. And handling it in a SQL standard way is cool for people that speak SQL. So we're doing that. And then the last 2 things that I think are cool are performance-related stuff. So vectorized query engine. It's operating on rows in chunks instead of 1 row at a time. And a garbage-free expression engine. So really, not trusting the JVM GC to really do an awesome job and just having an expression engine that doesn't generate garbage in the first place. So finally, try this at home. There's a few websites you can go to. So the current Druid community site is druid.io. Like I said, we're in incubation at Apache right now. It's a process. And at this stage in the process, we actually have a new community site up, druid.apache.org. Right now, it's just a button that takes you to druid.io. But at one point, that will change and go the other direction. So those are the 2 sites. I work at Imply, so I had to give a little bit of a plug for the company I work at. We have a distribution of Druid along with that UI I had screenshots of earlier. It's at imply.io/get-started. So Druid paired with a nice slice and dice interactive UI that lets you get super good value out of it. Also, we're hiring. If anybody wants to work on Druid, please talk to me after the meetup. Contribute to Druid. It's open source. We're on GitHub. So it's github.com/Apache/incubator-Druid. Come check it out. And then finally, follow us on Twitter. We do a lot of announcements on Twitter when when a meetup's happening, when there's a talk happening, when a cool blog gets published, when a release happens. So Twitter's a good place to get Druid announcements. And then also at druid.io/community. There's a mailing list you can join. So there's user list, a dev list, and also information just about if you're interested in contributing to the code, how that works, and how you can submit patches and how you can eventually become a committer if you're interested in doing that. And that's the last slide I have, so thank you. How much time do we have for questions? 5 minutes? OK, what's up? How durable are our historical segments? Great question. Very durable. So this slide over here, that line, in the interest of simplicity, I didn't draw a important part in between them. We call it deep storage. And deep storage, the idea is it's somewhere you put your segments. So the indexers write to deep storage, historicals read from it, somewhere that's durable. So it's either going to be a cloud storage like S3, or it's going to be HDFS. So even if every historical dies, you just throw a bunch of TNT in there and blow them all up, you can spawn new ones, and then the new ones will be able to pull stuff from deep storage. So it's all still there. So the question was, what about using memory to speed things up? So we do that. So Druid memory maps all of its segments. So the idea is the historicals prefetch segments from deep storage. They're already on disk by the time a query happens. We never involve deep storage in the query path. So it's never going to hit S3, never going to hit HDFS. It's always going to be hitting local. And it's memory mapped, so the OS is able to cache stuff in page cache if it can. And because we're column-oriented, all the pages for a certain column are together. And so that, if you're not using a column, it won't be in memory. And likewise, if you have enough memory to store all your data, it will all be in memory. What's up? So the question was, is there a way to delete data for possible GDPR or other reasons? So the segments, like I mentioned, are immutable, and that's for performance reasons. And the way you delete data in immutable segments is you create new segments that don't have the data that you don't want. And we do support that. Druid actually has a atomic update functionality where you can do basically a bulk operation, so bulk filter, bulk transform, bulk delete, and generate new segment files that are modified in the way that you want. And when the new ones are ready, they replace the old ones atomically. Any other? Oh, what's up?
Actually, he told me the question, but regarding that, have you ever thought of using, let's say, Vertica, which is another analytical database, using delete vectors, meaning the segment is still immutable, but you add another very small segment that maps which records needs to be are in fact deleted, and then you join them in the query, on the query in the reading level, so you don't need to compact the segment in order to get a new one with the deleted data.
Yeah, so the question is, have we considered using delete vectors like Vertica does? And I think that Apache Kudu does something similar. I think they have like a little update log that goes next to their segments too. So we don't do that in Druid. It's something that I think, community-wise might make sense as a optional feature. The reason we didn't do it in the first place, the reason it's not part of the original design is because we put a really, really high priority on the segments being immutable and interchangeable and being able to balance them however we want. So the idea is that if you add new Druid servers or remove servers, those segments get moved from server to server really aggressively to try to balance load. So, if there's a hotspot in the cluster, we try to get rid of the hotspot. And those kinds of balancing operations can be a lot more flexible if they don't have to move around update vectors and delete vectors. So that was the motivation. There's use cases where you care less about rapid balancing and you care more about being able to do point deletes, and I don't know, could make sense in the future. Yeah. What's up? Yeah, so the question was, I said Druid does limited kinds of joins. What do I mean by that? Okay, so Max will be talking more about that. I will say a couple words, which is we support a function called query time lookups that basically imagine a lookup table key value map that gets distributed out to every server. And that is the functionality that we use instead of doing joins. It satisfies use cases where the table you're joining against is small and can be broadcast everywhere. Any other questions? Oh, what's up? The question is, does Druid SQL have a query optimizer? Yes, Druid SQL is actually based on Apache Calcite. And Apache Calcite has a really nice query optimizer, and we totally piggyback on that. What's up? The question was, is there a Spark connector that takes advantage of indexes in Druid? There's a couple ways we can interact with Spark. So there is a optional module in Druid that can bolt on a Spark streaming and load data into Druid. I know that's not what you asked, but I'm saying it anyway. And what you did ask about Spark using Druid indexes, so I think I forget if it's on the Druid.io GitHub or the Imply data GitHub, but one of them has a Hadoop input format that knows how to read Druid segments and knows how to pick out the columns it wants and knows how to use those indexes for filtering. And Spark can use Hadoop input formats, and you can use that Hadoop input format in Spark, and it will be able to use the indexes. I don't know of anybody doing anything in production with that, but I played around with it one time, and it was kind of fun. So I guess there you go. Anything else? What's up? So the question was, I guess I'm butchering this, but schema-lite, how does it work? The way that it works is that in Druid, there's no concept of a schema for the whole table. So actually, it's all reconciled to query time. So the table itself doesn't have a schema that applies at ingest time. The ingest time schema only applies to new data that comes in, and each segment does have a set of columns it has in that segment, but there's nothing that says every segment in the same table has to have the same columns. So the schema-lite functionality works by let's say you add a new column, new data comes in, the segments for those new time ranges are going to have that new column in it. The old segments won't have the new column. They're going to stay the way they are. They're going to remain immutable. Nothing's going to touch them ever. At query time, it gets reconciled, and the way it gets reconciled is segments that don't have that column, it gets treated as a null. Anyone else? All right. Thank you again.